Okay, welcome to inductance video, inductors, induction video number 4. Last time I introduced a circuit element called an inductor, and I wanted to draw some parallels here between inductors and other circuit elements that we've already studied. First circuit element we really thought about was, actually we probably did capacitors first. I don't know. So we have these definitions for resistance and capacitance that we've dealt with multiple times in the past. And there is a similar definition that we saw in the last video for inductance. Notice that I've written the definition here in the style without the big N, but I did put a little total subscript on the flux just to make you think about the fact that the number of turns is a part of the flux there. But all three of these definitions are based on the way the device operates or behaves, right? With resistance, it's the ratio of the potential difference to the current. How many volts do you get when you put a certain amount of current through the device? It makes no difference what the device is. You could calculate an R value for literally anything. All you have to do is know how much current is flowing through it and what the potential difference is. Capacitance, similarly, oh, I wrote the wrong definition there. That should be Q over delta V, not Q over C. For capacitance, it is how much charge you need for a certain voltage. How many coulombs per volt. So again, it doesn't really matter what the device is actually made of, whether it's a parallel plate capacitor or something else. Just looking at how much charge is accumulated and what the potential difference is. So then, similarly for inductance, all you have to do is measure the amount of flux that passes through a device relative to the amount of current flowing through it. And then below, I have a set of formulas which are based on particular device designs, idealized device designs. So for resistance, this formula is about, the resistance basically of a wire of some sort. You need to know the resistivity, rho, of the stuff that you made the wire out of. It's a material property that you would look up in a book somewhere. And other than that material property, it's just physical measurements. How long is it? How wide is it? And you can calculate a resistance based on that as well. For capacitors, we have this similar formula. There's a material property part where you need to know the dielectric constant K. And that's for whatever stuff you put between the plates. And then there's physical measurements. What's the area of the plates? How far apart are they? And for an inductor, we have a similar formula. The idealized inductor is a solenoid. So you need to know physical things about it. You need to know how many turns or how many coils are there. You need to know the area of those coils. You need to know the total length of the device. And as I mentioned, if there's something other than just air inside the coil, then you would replace this mu naught with mu for that substance. So there's a material property component to this one as well. So I'm going to talk about mostly about one, but two additional types of circuits that include inductors. First, I want to explain or kind of restate the basic behavior of inductors and circuits. This is all ideas that I went over in the previous video. Mathematically, what we've got is this stuff on the first couple of lines. The AP formula sheet gives you this information, I think these are on different lines on the AP formula sheet, but both of these statements are there. That EMF is negative d phi dt. Again, they don't include the big N. I put a little subscript tote on there, but the College Board doesn't. They just write phi. So that's one thing they tell you. And then they also tell you that EMF is negative L di dt. But from those two things, you can conclude that, oh, well, phi must be the same thing as L times I, which is the definition of inductance. So they don't have the definition on the formula sheet, but if you were to need it, which is unlikely, but if you were to need it, just look for these two different EMF statements that they have near the end of the E&M block, and you can reconstruct the inductance from that. So the key idea for inductors is that they generate an EMF in response and in opposition to changes in the amount of current that's flowing through the inductor. So if your circuit is in some sort of a steady state, if it's been in whatever state for a very long time, the current level is probably constant, possibly even zero if it's off, but if it's on, you have some constant amount of current. And in that case, the ideal inductor does absolutely nothing. The potential difference on the inductor is going to be zero because it generates EMF only when there is a change in the current. The EMF is proportional to di dt. So if I is constant, it has no EMF, and so the potential difference that you would measure on it is going to be zero. So you can basically just pretend in a steady state that the inductor is just more wire. An idealized, again, this is for an idealized one that doesn't have any resistance. If the coil has some resistance, then you'd have to do like a V equals IR thing for it to get the delta V, but ideal inductors have no resistance. Okay, so that's for the steady state. But if you try to do something, if you change the current level in the circuit, in that initial moment, like at time zero, the inductor is going to jump into action, and it's going to maintain the previous current instantaneously at t equals 0. It's going to maintain the previous current. And it does that by adopting whatever EMF is needed in order to maintain that. So the simplest case would be, like, suppose I have a 9-volt battery and some stuff and my inductor. If I just turn off the battery, then the inductor is going to suddenly replace it by being 9 volts. Now it's not going to last. The EMF of the inductor will start to drop immediately, but instantaneously at time 0, it's just going to pick up the slack that the battery had, whatever that voltage was. So that's only instantaneously, again. So over time, the EMF gradually drops down to 0, and so the current will asymptote towards whatever value you were trying to make it have in the first place. So if you're turning off the system, the current will go down to 0. If you are just turning on the system, the current will increase to whatever current you would get based on, the voltages and the resistances and that sort of thing. So that's the basic idea. Many questions that the College Board asks about inductor circuits, those are the only ideas you need to answer them. They frequently just ask things like, what happens at the very beginning and what happens a long time later? So let's look at a specific layout. I have a circuit here that includes a switch so that I can flip it back and forth to both charge and discharge the system. My circuit has a battery with an EMF E, it has a resistor R, and it has an inductor L. Notice that the symbol for the inductor in the diagram is this curly Q shape. And that's just to make you think of a solenoid, basically. So you can tell it's a coil. And because this is a circuit that has a resistor and an inductor, it is called an RL circuit. Just like an RC circuit has a resistor and a capacitor, this has a resistor and an inductor. So I want to think about charging this up. And I'm using the same language as I would for an RC circuit there. In the moment that I first turn it on by putting this switch in this left position, so I've closed the switch, connected everything to the battery, current should start flowing. But because of the inductor, at t equals 0, instantaneously, the current is still going to be 0. The potential difference, if I were to measure the potential difference on the inductor at that instant, it would be negative E. Has the same magnitude as the battery's EMF, but it's oriented oppositely so that current doesn't flow. But that EMF is going to die off, and so if you wait a very long time, eventually the current is going to become E over R, which is what you would get just using resistance ideas. I have this EMF E, I have this resistance R, so the current is E over R. And in that final state, after a long time, the potential difference for the inductor is going to become 0. And during that entire process, as the current is increasing, the current is initially 0, and it's building up to this final value of E over R, the magnetic field B inside the inductor is also building up or increasing as this goes, because the magnetic field in the inductor is proportional to the current. So as the current increases, the magnetic field also increases, approaching some final steady state value. So if I were to make a sketch of how the current fluctuates over time, it would look like this. And that should remind you of a bunch of the graphs that we used to draw for RC circuits. That is not a coincidence. And I'll get to that in a moment. The math for the discharging case is easier, so I'm going to do that first, and then we'll come back to the charging case. But here's the discharge case. So we're going to presume that it was in that previous state for a long time. I reached my maximum current, everything was steady. And then I took the switch from that left position and moved it over to the right. So now there's not a battery in the circuit anymore. I just have a loop with only the resistor and the inductor. In the moment that I do that, at t equals 0 instantaneously, the function of the inductor is going to be to maintain the current that had already been flowing through it. So I know the current was going clockwise through that loop, which means that the current through the inductor was going down. And so when I throw that switch over, the current continues to flow down through the inductor. So the current is going to go around this loop in the same direction through the inductor that it already had been flowing. So again, the magnitude of that current at time 0, instantaneously only, is the same value that it previously had. I know that it was moving at E over R, and so I still have that same current. And the only way for that to be the current is if the potential difference on the inductor is equal to the EMF of the battery that I just removed. Now, if I wait, the current's going to gradually die out. So if I wait a very long time, t equals infinity, the current has to go down to 0, because there's not a permanent energy source here. So the current eventually is going to go down to 0. And once the current levels off, becomes constant, then the potential difference on the inductor is going to be 0, because you only have a potential difference on the inductor while the current is changing. So once it reaches its final value, the inductor no longer has a potential difference. Throughout this whole process, the magnetic field in the inductor is decaying back down to 0 because I started out with current, and so there was field. But as the current dies away, the field weakens, and eventually there's no field left. If I were to sketch a graph, it would look kind of like this. Again, that should look a lot like graphs that we drew for RC circuits. Again, it's not a coincidence. And what you're looking at there as the current dies out is the same thing as the magnetic field dying away. Just like with a capacitor, you have an electric field in a capacitor, and as that field gives out its energy, current flows for a while until it dies out. Same thing is going on here. It's just a magnetic field instead of an electric one. So on the bottom half, I've got the math for this. This first equation is a Kirchhoff loop rule. So 0 equals the sum of the various potential differences. So if I'm doing this loop, that same loop that the current's flowing through, the first term is the potential difference for the inductor, which by definition is negative L di dt. And then the potential difference for the resistor, since I'm looping around in the same direction as the current, potential difference for the resistor should be negative, and it's negative IR. So immediately, as soon as I write that loop rule, you can see that I have an equation that contains I, which is a function of time, and the derivative of I with respect to time. So this is a differential equation. If you rearrange things a little bit, you can make it look like this. di dt equals, I need a minus sign on there. di dt equals negative r over L times I. What that tells me is that this function I of t, whatever the function is, if I take its derivative, I get the original function back along with some negative constant. That's exactly the same way it worked out with capacitors. The solution to that is some sort of an exponential function based on e. So if you take, and with a negative exponent. So if you take the derivative, you get the original function back, plus a negative constant from the chain rule part when you differentiate the exponent. So the current as a function of time is this decaying exponential. The initial or maximum value for t equals 0 is e over r. You can also just think of that as I naught, like whatever the initial current is. And just like with an RC circuit, you can take these pieces that are up in the exponent along with the t, and you can turn them into a time constant tau. In this case, the time constant is L over R. With an RC circuit, the time constant was R times C, and this time it's L over R. So that could potentially confuse you, can mess you up, but it still has a time constant. Now, if I go back to the charging case, when I write the loop rule for the charging case, it's more complicated because the battery is there. So like if I do this loop, that's the direction the current's flowing while charging. But there's 3 circuit elements here instead of just the 2. So I need the battery, I need my minus IR, negative because I'm going with the current through the resistor, and then I need negative L di dt. This time the minus sign is intrinsic, it's part of it all the time. So setting this one up to solve or to examine is not as obvious that the solution is going to be exponential again, but it still works out to be exponential. It ends up looking just like the formulas we had for RC circuits. You have your maximum value as some sort of a coefficient, and then you have 1 minus e to the negative x. And all the other stuff still applies. So if you encounter RL circuits on the exam, you need to know that they have an exponential growth and decay behavior. You need to know that the inductor at time 0 is going to maintain the previous current, and that at time infinity the inductor is basically just wire. It's unlikely that you're going to have to do any of this differential equation stuff for RL circuits, but you might have to. Usually if they want to do this, they do it with an RC circuit instead. Like, you don't even see inductors every single year. Inductor circuits, at least. You don't even see that every single year on the exam. But RC circuits you basically always see. Now, to make another comparison to capacitors here, inductors are energy storage devices, but as I mentioned before, they store their energy with the creation of that magnetic field instead of with the creation of an electric field. So if you take that loop rule equation that I wrote for the charging case with the battery and everything else, I like rearranged it so they're not all on the same side anymore, but that's still the same loop rule equation. If you just multiply the whole thing, multiply the entire equation by I, you get the line that I have below it. And there's some interesting stuff here. I squared R, I know that that is the power consumption of a resistor, power of the resistor. And E times I, we're a little bit more familiar with I delta V, but that's also a power. That's a power expression you can use for anything, including, for example, the battery. Since E is the voltage of the battery, this has to be talking about the power usage or power provided by the battery. And so we have this other term here, which has to be a power, and the only other thing in the circuit is the inductor, and it already has L in it. So that expression must be the power use of the inductor. That is the rate at which energy is being deposited into the magnetic field of the inductor. So if you want to know how much total energy ends up getting stored, you can just integrate that. The integral of a power is a time, because power is the rate for energy. So the energy stored in the inductor, U sub L, it's got to be the integral of that expression with respect to time. That expression has this di dt in it, so if you strike out the dt's, it becomes an I integral. And so you just imagine your initial current being 0 and your final current being whatever your final current is. Integrating L times I di gives you 1/2 Li squared. So this expression for the energy in the inductor that is on the formula sheet, you don't have to create it from scratch. But that's where it comes from. The easiest way to get it is with this loop rule. Okay, and the last thing is that I want to incorporate a capacitor into all of this. So if you make a circuit that has inductor and capacitor, it's called an LC circuit. And the thing, you're very unlikely to have to do any math at all for an LC circuit, but you do need to be familiar with their existence and the basic idea here. We know that RC circuits and RL circuits both have this exponential growth and decay behavior. We know that both of them allow you to store energy temporarily in either the capacitor or the inductor. In one case, the stored energy is based on the accumulated current, Q, right? You send a bunch of current into a capacitor, gradually build up the energy, and then you stop sending current in once it's done. But in the other device, the energy storage is based on how much current is flowing instantaneously. So one of them is based on the accumulated current, the other one is based on the current. So they're storing the energy in different ways, but they're both related to the current. So what ends up happening is that the energy oscillates back and forth between the two devices. I have a schematic drawn here that has only the capacitor and the inductor, so there's not even a battery here, just to keep it as simple as possible. But imagine that magically I made some current flow through it at some point in the past. I used my telekinesis or my metal bending to make some electrons start to flow, and so there was a current. Once that current is established, the current is just going to oscillate back and forth forever. We can get some math behind this. Again, you probably will not have to do this math, but I know that the total energy in the circuit has got to be the sum of the electrical energy and the magnetic energy. The energy in the capacitor I could write this way, Q squared over 2C. The energy in the inductor I can write this way, Li squared over 2. So if I take the derivative of that whole equation, I know the total energy should be constant. So d by dt of the energy U is 0. If I take the derivative of the capacitor energy, do my little power rule, so I'm going to get 2q times q prime over 2c. That's this. When I take the derivative of the inductor term, I'm going to get 2li I prime over 2, which is this part. You can cancel some stuff out, and then keep in mind I is the same thing as q prime, and so I prime is q double prime. So I've got a lot of q's here, but both of the terms have q prime, so we can cancel out the q prime. That leaves me with an equation that has q and q double prime. If you solve for q double prime, you have this. And this differential equation is the same one that we saw for simple harmonic motion back when we were studying mechanics. If you see second derivative of thing equals negative constant times the original thing, the solution is sines and cosines. It's a periodic function, just like simple harmonic motion. The coefficient for t, the angular frequency that you have to put into the sine or cosine, is always the square root of whatever this constant is. So I know that I have to do square root of 1 over LC in there. So the frequency, the angular frequency at least, of the oscillations is 1 over square root of 1 over LC. Again, the math you probably are not going to have to do, but you do need to know that a circuit that has capacitor and inductor is going to be an oscillating system. It could be that that's the only thing that they ask about it. They might say, what is this circuit going to do when you turn it on? The answer is, it's going to oscillate. Now, my last slide is an attempt to kind of illustrate the process of the oscillations. It's probably not critical for the exam that you understand this, but it might help you to get a better handle on what's going on. So in the top picture, you can think of this as the starting case. I have the capacitor charged up. You could imagine maybe I had charged it with a battery and I've just now removed the battery or something like that. So it's in its like maximum charge state with the top plate being positive. The electric field is at its maximum. And in this moment, because I have just finished charging the capacitor, there's not any current flowing. So I equals 0. Since there's no current, there's no magnetic field in the inductor. But as soon as I, let it go, the capacitor is going to begin discharging. Current is going to flow away from the positive plate. It's going to go around. And that's what I'm illustrating in the second picture here. So the capacitor is going to drain itself out with this clockwise current. The current will be at its maximum value when the capacitor has just completely emptied itself out to an electric field of 0. And when the current is at its maximum, the magnetic field in the inductor is also at a maximum. And you would think, well, at this point, the whole thing should stop because the capacitor is now empty. But the capacitor itself is not providing a potential difference anymore, but the inductor, as the current starts to die out, the inductor is going to develop an EMF, a forward EMF, to keep the system going. So current will continue to flow through the inductor in the same clockwise direction. And as that current continues to flow, we're going to start building up an opposite charge on the capacitor from the way we started. So the capacitor has passed through an electric field of 0, and now we are building up the electric field the other way. So now the bottom plate becomes positive. We gradually fill up that plate until the magnetic field has completely died away and can no longer provide an EMF. And then the current flows back out the other way again. So it flows one way for a while, powered by the capacitor. Then it continues to flow that way, powered by the inductor. And then it turns around and goes back the other way. Again, first by the capacitor and then by the inductor. And then the last little piece I want to mention is that if the circuit also has resistance, then it's called an RLC circuit instead of just LC. And instead of a simple harmonic oscillator, then it's a damped harmonic oscillator. The resistor gradually dissipates energy. So it's still going to like cycle through, but the amplitude of the oscillations gets smaller and smaller over time until the whole system stops. And that is it. So again, when it comes to LC circuits, most important thing is that you just know it's an oscillating system. And when it comes to LR circuits, the most important thing is that you know the behavior is going to have these growth and decay patterns, similar to the way RC circuits work. And you're most likely to encounter questions about time 0 and time infinity. And you just need to remember at time 0, the inductor maintains whatever situation had just been going on. And you should be able to reason through almost everything that they ask based on that. And that is it. That is the last piece of content that we need. Yay. So the rest of the remaining weeks that we've got will be various test-taking strategies and practice tests and that sort of thing. But the content is done.